Hi, good afternoon, everybody. My name is Wei Wang, Associate Professor of Computer Science, College Science. And today is my great honor and pleasure to introduce my colleague, Dr. Hajar Homayouni, to give a talk. And Dr. Hajar Homayouni is an Assistant Professor of Computer Science at San Diego State University. She received her PhD degree in Computer Science from Colorado State University in 2021, this year. The main focus for her research is to automate the process of detecting and explaining anomalies in big data being used by data analyzers to make critical decisions. In addition to her academic experience at San Diego State University, Colorado State University, and Azhar University in Tehran, she has several years of industry experience, particularly in software research and development. So now today, please welcome Dr. Hajar Homayouni for her talk on anomaly detection and explanation in big data. Thank you.
Thank you so much for the introduction, and thank you all for attending this presentation. I'm going to talk about my PhD work, which was on anomaly detection and explanation in big data. I will also talk a little bit about my current project that I'm working on. So this project was basically started about 2 years ago, and there was a lot of interesting patterns that we found out in the data, and I thought it's a good time to present it as we are dealing with a very complex data set and big data set today. So the outline of my presentation is first I'm going to give an introduction and talking about the related works in this area. Then I'm going to give examples about what the goals of my research is and what is the basic problem that the research is going to address. After that, I'm going to talk about the proposed framework as well as evaluations, and finally, I will conclude this talk and talk about the future. Please just stop me anywhere if you have some questions. Today, as you are aware of, every enterprise is dealing with data. They store the data in different dialects, like big data dialects on the cloud and on the data warehouses and data lakes to make critical decisions and to do different types of activities. As the quality of the data directly affects the quality of the decisions that they make based on the data, it is very important to thoroughly test the data. So, however, the data in these types of storages may become incorrect or invalid because of different reasons, such as how the data is collected, how the data is transformed and loaded to these dialects, as well as sometimes because of malicious activity. So testing the data is very important. Before talking about data quality tests, let's see what are the different types of data we are dealing with in the data storage. We are dealing with non-sequence versus sequence data. And a non-sequence data set is a set of d-dimensional records. And these records are not dependent to each other. They are totally independent, and their order does not matter. An example is a breast cancer data set that contains values of tumor size for different patients. These values are independent from each other. On the other hand, a sequence data set, an example is the time series data set, is a sequence of d-dimensional records. So in this data set, the order does matter. So these records, for example, can be captured over time, and there is a temporal dependency between those records. So in this case, if the dimension of the data is equal to 1, we call it as univariate time series, and otherwise we call it as multivariate time series data. Now let's talk about the data quality test. Data quality tests in general validate data that is stored in any of the storages to check the data against some rules. These rules are called constraints, and those constraints are typically imposed by the domain expert or the data model that is used to describe the data. You can see some examples of constraints that can be over different entities in a data storage. They can be defined against a single attribute or a single feature of your data. For example, if you have a climate data set, you say wind speed must be positive. It can be defined over multiple attributes as the relationship between those attributes. For example, in a vehicle data set, you may say if vehicle speed is a positive value, then the RPM also must be a positive value. So you say that these are relationships between multiple features, and it can also be defined against or over multiple records in your data set. So specifically for the sequence data set. For example, patient weight growth rate over time for the infant patient must be positive and in a specific range. So it can be even more complex. It can be defined over multiple records as well as multiple attributes. Like in an electricity data set, the mean value of daily delivered electricity to a specific type of premise, which is residential, must be in a specific range. So you see these constraints can get more and more complex. One of the issues that exist is domain that should define these rules, and they are typically doing it manually based on their requirements. So let's see what are the limitations of the existing approaches. There are two groups of approaches. The first group are based on a pre-specified constraint. Like I said, the domain expert typically write those rules and check the data against those rules. In this category of approaches, there are two types of approaches. One is domain independent. So these approaches are based on some very trivial or basic rules, such as uniqueness check or not null check, that can be applied to any domain. An example is an informatical tool. Another set of approaches are domain specific. So those are the approaches that, for example, the medical expert for the health data has generated or has, wrote those rules to be checked against the data. Examples are Academy and PetNet tools that are available online for the health data. The other category are based on discovered constraints. So these are AI-based approaches, and these approaches automatically discover those rules using the data. There are some limitations with those approaches. These are typically called anomaly detection approaches. First of all, they just report the existence of anomalous data in a data set. They don't explain the reason behind invalidity of those data points. Most of the time, these approaches are supervised, which require labeled data, and in big data sets, accessing and providing labeled data is almost impossible. And they are also prone to generate false alarms. For example, there are some unsupervised approaches. They don't know about the validity of data in advance, but they are prone to learn the incorrect constraints from the unlabeled data and generate false alarms. So the problem that my research answers is to automatically detect and explain anomalies that are missed by domain experts from unlabeled data in any domain. So this is actually the question that my research has been trying to answer. So the objective has been to develop a domain-independent automated data quality test framework, we call it as adequate, that can discover complex constraints from any data, both sequential and non-sequential data, that can report as suspicious those reports that do not satisfy the constraint. Why I said suspicious and not anomalous? Because some of the times the record that do not follow some rules are not necessarily anomalies. They may be, for example, in a health data set, there may be some patients with diagnosis of cancer or some different behavior from the majority of data. So we call it as suspicious. And we also explain the constraints that are violated by the detected suspicious records. Finally, our approach minimizes false alarm over time through an interactive learning process. So in this process, we take feedback from the domain expert to retrain the machine learning model and improve its accuracy over time. Here is an overview of the adequate framework that we have developed. It has 5 different components. It takes the data in raw format as input, and it reports some groups of suspicious records, as well as some explanations about those. So let's talk about each component. The first component is data preparation. It just transforms data from its raw form to a form that is suitable for analysis. The second component is constraint discovery. It is where we're using a deep learning model to training against the big data and to best represent the constraints that are in the data. The anomaly detection component detects those records or subsequence of records that do not follow the discovered constraint. So this component is actually used the trained model. The anomaly interpretation is where we generate some visualization diagrams to help the domain expert understand why those records or those subsequence of records have been detected as anomaly. And finally, the anomaly inspection component is a web application where we show the domain expert the detected anomalies, and they can flag as faulty those groups of records that are actually anomalous. This information is given to constraint discovery component to retrain the machine learning model and improve its accuracy over time. So I'm going to talk about this component in further detail in the coming slide. So before that, let me tell you that we have instantiated this framework to generate applications for both non-sequence data and sequence data. The first step, we generated adequate 2, and it was only for the non-sequence data. And we have published some of the results in this papers that are listed here. So let me describe how adequate 2 has instantiated each component of the framework. So the first component is the data preparation component. And for data preparation, we use different techniques to modify the data in a manner to make it useful for analysis, make it in a form that is suitable for analysis. So in general, machine learning algorithms typically cannot work with raw data. They misinterpret it. For example, if you have some categorical data, they may be interpreted as numeric data, and there will be a natural ordering assumed for that data. For this purpose, we have transformed categorical data into a new form, which is a binary data, as you can see in the figure. So in this figure, there is a color attribute with different values for the color, and it is encoded to 3 new columns in the data set, which are binary, and for each record, only the color that has the value, for example, in this case equal to red, will be 1 and other will be 0. So this way, the natural ordering that the machine learning models that may assume for the data will not happen. The other approach that we used was min-max scaling, and this is for numeric attributes. And so numeric attributes with high magnitude and range may carry a higher weight in machine learning calculations. So we want all of our attributes to be at the same level of significance when we want to train a machine learning model. That is why we are using rescaling approaches to make all of our numeric attributes to be in a specific range. For example, example, between 0 and 1 in this example. So after data is prepared, the next step is to discover constraints from the data. So in this, in our framework for the non-sequence data, we have used a deep learning model called autoencoder. So what autoencoder does is actually it regenerates the data based on itself. So it regenerates data, and the data that does not follow the pattern of the majority of the data set, their regeneration is different from what is expected. And that way we can figure out whether that data is anomalous or not. In this figure, you can see the structure of this deep learning model. It takes the data as input. The data has few different features and few different attributes, and it's reconstructed in the output. So X prime is the reconstruction of the input. It has two components, an encoder and a decoder. The encoder maps the input into a representation, which is a nonlinear combination of the input attributes. So this new representation can be assumed as the constraints that are discovered in the data. And the objective of decoder is to confirm that the new representation is correct. For this purpose, it reconstructs the data from the new representation to regenerate the data. And this model is trained to minimize a reconstruction error, which is the difference between the actual input and its reconstruction. So as you see, the constraints are in a very complex equation, nonlinear equation, which cannot be interpreted by human beings. That is why further steps are required to describe this equation to the domain expert. And this reconstruction error can be considered as a identifier of an anomalous data. So if the data is anomalous, this reconstruction error is a high value, because the network, which is a representation of the pattern of the majority of the data, have not been able to regenerate the data. So that is why the reconstruction error is used here for the detecting anomalous data. So in the anomaly detection component, this trained autoencoder is used, and by the way, the autoencoder model is unsupervised. The data is not labeled. So the trained autoencoder is used to assign a suspiciousness score to each data record. And the suspiciousness score is calculated based on the reconstruction error that we just talked about. So those records whose scores are greater than a threshold are flagged as suspicious. Now let's say we have a very big data set and the number of records that are detected as suspicious are huge. So asking the domain expert to inspect those records, it will take forever, and typically domain experts do not have that much of time. So that is why we use, yeah.
The domain expert is a person or is it a computer?
It's a person. So I'm talking about, for example, a medical expert. Yeah. So for this purpose, yes.
I have a quick question. The detection score, is that, how is that threshold gauged, and is it dependent on each data set?
So for the threshold, we use approach based on standard deviation of the data, and it is, what was the second question?
Oh, and is it dependent on each data set?
Yes, it is.
Okay.
Yeah, it is dependent on how the distribution of things and the data. So that is the threshold, how the threshold is set. And so based on those values that are outside that threshold, we decide about the suspicious. So like I said, the number of these records may be too large to be feasible for a domain expert to inspect them. That is why we use a clustering technique to group those records based on their similarity. And so all the records with the same features will be in the same groups, and it will help domain expert to inspect those groups in a faster manner. So we have used self-organizing map clustering technique. And why we use this technique? Because it preserves relationships among the attributes. So the way that it clustered the data, it considers the relationship between the data attributes. That is why this is a good approach for our problem. In the next component, where we want to interpret the anomaly data to the domain expert, we generated two plots, two visualization plots. The first one is suspiciousness score per attribute that we have generated it based on the trained model. What does it mean? It shows you the contribution of each field or each attribute in the invalidity of that group of data. For example, if you have a group of data, you say that attribute X and attribute Y are the major causes of invalidity in this group. So it will help the domain expert to focus on the invalid attributes in case there are, let's say, hundreds or thousands of attributes in your data. Another diagram that we generated are decision trees that are extracted from a random forest classifier trained using valid and suspicious records. So when we use autoencoder model and that threshold value, we were able to label the data into suspicious and non-suspicious. Using that labeled data, now we were able to train a random forest classifier, which is a supervised learning technique, to generate some decision trees, and decision trees are human readable. So these are easier for human or domain expert to understand the kind of rules that are violated by the anomalous data. Here's a simple example for the health data. So this is a suspicious group detected from health data. This is for drug exposure data. So in this table, you see that there are two drugs that have been detected as anomalous. And the first plot, which is the suspiciousness score for each attribute, shows the contribution of each of these attributes in the invalidity of this group. For example, because these two attributes have a larger suspiciousness score, we say that these two are major causes of invalidity in this simple example. And the next plot is the decision tree, where it describes the rules that are being violated by those attributes. So it is not enough to know what attributes are invalid. We want to know what kind of rules are violated. So for example, it said if the drug unit is tablet and drug road is topical, label 1 means an invalid data. So this is showing what kind of rule is being violated. So every pass from the root node of this tree to the leaf node of this tree is describing a rule in the data. Finally, the anomaly inspection component is where we are moving from a totally unsupervised approach to a semi-supervised approach by incorporating the expert feedback into our model. So we use a new label input as the input of our autoencoder model, and this label input is updated based on the expert feedback. So for example, the label of the first training phase, where we don't have any prior knowledge about the data, this label input is equal to 0. After the model detects some of the records as suspicious, the label is updated to 0.5. Then when the domain expert confirms that those suspicious records are actually anomalous, we label them as 1. Otherwise, if they confirm that these are valid, these are just some abnormal but valid data, we set the label to -1. And we retrain the model. The reconstruction error that I talked about is redefined based on the value of the label. And as a result, the suspiciousness score that is calculated is redefined based on this label value. So we evaluated the adequate tool with different objectives. First, we evaluated the anomaly detection effectiveness when we don't incorporate domain expert feedback in just one execution of the tool. After that, we evaluated the accuracy improvements of the approach over time after we incorporated the expert feedback, and we also evaluated the anomaly interpretation effectiveness as well as the performance in terms of time. For this purpose, we use some of the existing standard metrics as well as defining some new metrics. For example, the true positive rate, false negative rate, true positive growth rate are some standard metrics that can be used to see whether the approach is accurate enough in detecting the anomalous data. We also define this visualization efficiency as the percentage of visualization diagrams that can correctly explain violations, and we define this focal time to evaluate the performance of the approach. The subjects that we used for this study were based on both real-world data sets as well as some available data set on UCI ML repository. So if you look into the real-world data set, they were pulled from the plant and health domain. The health data set was from Health Data Compass at Anschutz Medical Campus at University of Colorado, Denver. And this data set included data from UC Health as well as Children's Hospital of Colorado. The other data set was from the Plant Diagnostic Clinic database at SDSU, or Colorado State University. So the UCI ML datasets were from many different domains, including oncology, immunology, health, biology, etc. So we wanted to show that our data is our approach is domain independent and can be applied to different data sets. Here is a summary of results. It took between 0.1 to 26 minutes for the data set under test to run the approach. So depending on the size of the data set, which kind of has a linear relationship between the size and the time. For the real world data set, most of the anomalies that were previously detected by the existing approach could also be detected by our approach. So what I mean by existing approach is the approach that we're relying on domain expert to define the constraint. So comparing our approach with those manual approach, we could detect most of the approaches. There were some new anomalies that were detected and were not previously detected by the existing approach. So it shows that our approach could generate or discover some new constraints from the data. And in general, between 53 to 100% of the visualization plots were correct explanation of violations. So when we looked into the detailed examples of this plot, the decision trees were more useful than the suspiciousness score per attribute. And we use UCI machine learning data set to observe the accuracy of approach improvements over time, and both true positive rate and false negative rate improve over time after using of feedback from the domain. So the second instantiation that I will talk about is ideal, and this is for sequence data. We call it as ideal because it's an approach for interactive detection and explanation of anomalies using an Lstm autoencoder method. And we have published the results in this paper. So before talking about this approach, let me give you some examples of different types of anomalies that can occur in sequence data. So in a sequence data set, like I said, where the order does matter, there are two types of anomalies. One is anomalous record and the other one is anomalous sequence. Anomalous record is given a time series An anomalous record is one that its observed value is significantly different from what is expected. Here you can see an example in a health data set for infant patients. So, for example, if an infant has a weight value outside of a specific range, it might be reported as anomalous. So, if you observe how the weight value grows over time, and let's say you see a significant drop or significant increase, you can consider that as an anomalous record. An anomalous subsequent is a subsequence of record that have different behavior than the entire data set, than what is expected in that specific duration of time. For example, consider an intersection in the traffic data that has an upward trend from, let's say, 6 a.m. to 9 a.m. in the morning, and suddenly in your data set you find out a subsequence that has a downward trend or some different trend in that data. And so you see that there is something wrong, there is a different behavior than what is expected. This can be an anomalous data. This can be as a result of, for example, a snowy day, or I don't know, a holiday or something. So, but this is a different behavior than the expected behavior. It's called anomalous subsequence. So I'm going to talk briefly how ideal for non-sequence data has instantiated the different components of the adequate framework. So for the data preparation component, along with what we talked about for the non-sequence data, such as making categorical data or transforming categorical data and numeric data, we did another step, which is reshaping data in a manner that is suitable for analysis by the machine learning model. So for sequence dataset, we are using an LSTM or long short-term memory model, which is appropriate for sequence data, and it can learn the temporal dependencies between the data record. That LSTM model requires its input to be subsequences of data, be windows of the data. So we need to identify that subsequence as the input of the LSTM model. So this is also called the window size, and this length of this subsequence or this window size determine how far back the LSTM connects a record to its past value. This window size affects the correctness of constraint discovered by an LSTM model. And the existing approach typically select window size based on a fixed size window or by using an exhaustive brute force approach. So they try different window sizes and see which one results in a better accuracy of the model. In our approach, we use an autocorrelation based reshaping that adjusts this window size based on how far the records are actually related to the past value. So this is a step that is done prior to training the LSTM model. You can see the architecture of the LSTM autoencoder model that is used in this study. So if you look into the structure of this model, it's like the original autoencoder model. The difference here is instead of having a single record as input, we have a subsequence of records. So the input is a matrix. So these matrices are, for example, the W past records in the data set. The output is the reconstruction of the input. It is also has an encoder and a decoder. The output of encoder is a representation of as a nonlinear relationship between the input matrix, which include both attributes and record. And the output, like I said, the decoder reconstruct the representation, reconstruct the data using that representation. The difference, one other difference between this model and the original autoencoder is that it is using LSTM layers instead of the ordinal neural network layers. And LSTM layers or LSTM neurons have some structures within themselves that can learn long-term temporal associations between the data. That is why it makes them appropriate for sequential data. So they have something called memory cells as well as forget gates that will help them remember remember important information and forget non-important information in a sequence data set. So this model is trained to minimize a reconstruction error, which you can see is based on the difference between the input and output matrix. This sentence is what we have added in an interactive manner. So if you remember, I talked about sequence model. We have added a new input label to the autoencoder. In this case, the LSTM autoencoder has this new label, and this is updated based on the feedback that the domain experts give us. And this is how the reconstruction error is updated, the definition based on the label value. So for anomaly detection, we again define some suspiciousness score based on the reconstruction error and based on some threshold value that again is calculated with respect to standard deviation of the data set. We detect those records whose SS score are greater than a threshold, as well as those subsequences. So in this case, the subsequences also have some suspiciousness score. So not only the report have the subsequence have suspicious. So in the anomaly interpretation component, we generate the same plot that we generated for this non-sequence data, which is suspiciousness score per attribute. We also generated a visualization diagram that shows the contribution of the records in the invalid subsequence, not only the attributes, but also the records in the subsequence, as well as the decision trees that are generated using random forest classifier. So here is an example from the health data in the health data compass. They are for COVID positive patients. This is some of our recent research that we are doing, and for this purpose we have been using heterogeneous populations from different categories of patients. In this example, they are COVID positive males over year of 60, and we believe that their behavior should be the same. So this population with similar features should have similar behavior over time. For this purpose, we compare those patients that actually have some invalid, some have been detected by the tool as suspicious. First of all, we saw which attributes or which of the features are invalid. For example, for this specific data set that were lab results for the COVID positive patient, it shows that these two lab results are invalid for the subsequent. And also this plot shows a different behavior for a specific patient whose subsequent is detected as invalid. And the decision trees say what kind of behavior in the time series have been reported or have been violated. For example, the normalized mean of that specific test is something that is violated, and the moment tree of that specific lab result. So these are all defined in our paper. So if you're interested to learn about different characteristics of the time series that we explain in our rule violations, I encourage you to read that part of the paper. We also evaluated the idea with different goals. The goals are basically the same as the ones for non-sequence data. Most of the metrics that we use in this case are based on the a standard F1 score metric, which is actually an average over precision and recall. The subjects that we used were both real-world data sets as well as some data sets that are available online. For the real-world data set, we use energy data set from the Fort Collins, city of Fort Collins. So in that energy institute, there are, you see the number of records and the number of attributes of the data. So in those data sets, there were 0.05% of the records that were known to be anomalous. So we use that prior knowledge to evaluate our approach to see how many of those invalid data our approach can detect. We also detect both known anomalies and some injected anomalies in the data. By injected, I mean we use some mutation analysis technique to inject some faults to the data and see how many of those faults our approach can detect. We used a NASA shuttle data set from UCI Machine Learning Repository as well as Yahoo synthetic server data sets, and these are all available online. So for mutation analysis, we injected different types of faults to the data. We defined different operators for injecting faults. So these are basically the ideas from software testing. And if you are familiar with the mutation analysis and software testing, over there you inject some faults into the code of your software and try to see the test case, whether or not the test cases can detect those injected faults. In this case, we are injecting faults into the data. So for example, the first operator adds some noise, some random noise in the data to see if the approach can detect those. We also shifted the data, for example, with a horizontal shift or vertical shift to the data. We rescale the data, and we also add some dense noise into specific subsequence of data. So using those operators, we modified the data set and saw which one our approach could detect. So on average, it took between 152 to 593 seconds to run the approach against the data set. So that our approach took actually 152, and brute force approach we've been doing, which we wanted to compare our approach, took 593 seconds. So at the first step, because the injected faults were kind of complex to be detected, at the first execution of the tool, our approach could only detect a few of them, as you see. But after we use the information about the injected faults and retrain the model, then most of those faults could be detected. So the F1 score in terms of its growth rate, when we evaluated, we saw an improvement in the interactive learning approach. So our autocorrelation-based approach for assigning the window size was as effective as brute force approach, but it was 3.88 times faster than the brute force approach. And in general, some of the plots were not helpful, especially the ones that include complex equations in them. It was hard for the minister to understand, although we provided the explanation. But the suspiciousness score per attribute was more useful for them to understand the reason behind invalidity. In conclusion, we proposed adequate framework that can model complex constraints involving both nonlinear relationships among the sequence and non-sequence data sets. We detected suspicious records and sequences that do not satisfy the constraint, and we use explainable learning technique to interpret the constraint violation. Our framework could detect previously non-injected as new anomalies in data sets The accuracy of approach improved over time with the help of feedback from domain experts. And the autocorrelation windowing was an effective approach for reshaping the data. These are some of the other projects that we are currently working with. The first one is assessing integrity of COVID-19 data. So this is an ongoing project. We already published a paper in the Nature Computer Science Journal, and we still are working with our collaborators at the Anxious Health Data Compass to find out more interesting patterns in the data. The other project is effects of COVID-19 on energy consumption. So we analyzed how COVID-19 has affected the energy consumption in the city of Fort Collins in different sectors. For example, in residential, big commercial, small commercial, industrial sectors, how COVID-19 has affected the pattern or behavior of the energy consumption. We have submitted it to IEEE. And another project is on the security of heavy vehicles. We are doing with the University of Tulsa. So for this project, we are working for watermarking data, which is sequence data set, and for that purpose, we are using Lstm Layers. So if any of you are interested in any of these projects, I would be glad to form collaboration. So these are some of the works that I would like to work on here, I would say near future. One is complex big data quality assurance. By complex, I mean non-primitive data, including image data and text data, and a mixture of them. So how we can enhance the existing machine learning models to handle mixed data types. This is one project that I'm interested in working on. The other one is dynamic big data quality assurance, especially for real-time systems where we want to detect anomalies online. So this is requiring high performance computing, parallel computing, and big data on the cloud. Another project is human understandable report generation. So many of the AI techniques are not human interpretable. And this is a big question, how someone can understand the decision that has been made by an AI approach or by a machine learning approach. So the researchers in the Google Brain has started to work in this area and have some success to generate some interpretable information from the deep learning model. So I'm interested to work in this area as well. And finally, realistic synthetic data generation is another interesting project because as you may have seen, there is a lot of problems with confidentiality and privacy of data. And as data scientists or people who want to work in AI, we require data, and most of the time, this data is not available because of this concern. So it is important to be able to generate synthetic data that shows the features of real data. So for these papers, I will use some models like adversarial sampling techniques to generate some synthetic data for different purposes, such as validating anomaly detection techniques. So these are some of my recent publications, and thank you so much for listening.
Thank you very much, Hajar, for the wonderful presentation. Do we have any questions from the audience? Please.
So for the training portion for when you're doing the encoder and decoder, do you typically remove the anomalous data that you know about? Or is that part of the data set? Because I can see that as affecting it.
Sure. So why I call it unsupervised in the first step is I don't assume any prior knowledge. That is why I removed the label and I use all the data to train that model. That model itself will rely on the majority of the data set so the pattern of that is discovered by that model is based on the majority of the data. So the reconstruction error that is assigned to each record is based on how far is that record with respect to the expected pattern. And that is why I call it unsupervised. The thing that you said is called semi-supervised approaches. There exist some semi-supervised approaches that assume that their training data set is clean. So they have some prior knowledge, they clean the data and they use that data set to train a model. And then they use that trained model to detect anomalous data that come new. So for unseen data, it is used.
All right, I can follow up. So, and how do, between those two approaches, is there like literature say one's better than the other, or because I could just see the input of the anomalies into the training set to expand the standard deviation to make it harder to detect, from what I think, but.
Sure. So actually, one of the problems that we have with real-world data sets is that we don't know about the anomalous data. Even if they say that these data has anomalous, we don't know if it's the complete set of anomalous data. So assuming that the data is clean and training a model with clean data is something that is just based on an assumption, so it is not true all the time. We wanted our approach to be generalized enough to be applied to any domain, even if there is no prior knowledge about the validity of the data. So that is why we prefer to use the totally unsupervised version at the beginning or in the first iteration of the training, and then enhance the approach over time based on the feedback that we receive. Yeah, sure. Go ahead.
All right. Do you have any thoughts on how you can separate out the existence of anomalies from the issue of whether your compressive encoding is sufficient to handle the complexity of the data process?
So you say, I don't get your question. You say the constraints that are generated are not reflecting the actual complex constraints that are in the data?
Yeah, I mean, there may be some relations or features of the data that simply can't be detected because you compress the representation is too compressed to get it, so to speak. I mean, it seems like you're dealing with things where there's anomalous data that some expert can look at and immediately tell it's not, like a misspelling or a value of a sensor that's out of bounds, things like that. But there's an awful lot of applications of these sorts of networks where they're trying to perform really complex mappings to try to get much sort of. And it might not be obvious what's an anomaly.
Yeah.
Not.
I see. So I see your point. So one good thing about this deep learning models, they not necessarily compress the data. Sometimes the generated representation has even more features than the actual set of features. So what they do in comparison to some linear models, which they just can find out the linear relationships between data attributes, they can detect nonlinear complex relationships between the data attributes. So the challenge that I faced here was not the ability of the model to detect complex relationships. They could, but the challenge was how to understand those constraints. So even if there is a constraint violation, we don't understand it. So I have added a decision tree-based model to try to explain those violations. But that decision tree is independently trained with respect to those constraints, and that is why they may not reflect the exact complex relationship that is discovered by the model. So one of the challenges that I added to my future work is how I can extract that information from the deep learning model. This is a really hard problem to answer. Yeah, go ahead.
Yeah, so basically the question was basically the same because I think I'm not much in learning person at all. I'm just doing tsunamis. But the thing is, I'm thinking that when you are doing the encoder, basically you're trying to reduce the order of the problem that you have. You are trying to represent all these very long, a lot of points into a set of smaller order problems, which is basically your encoder. And I was having the same question. For example, if I'm thinking in a very extreme value analysis, in which, for example, you are analyzing earthquakes, and you have a very big earthquake, that is an anomaly, but in terms of statistics, maybe it's just because it's part of a tail of the same distribution, which is still valid. Yeah. It looks like an anomaly, but basically it's because in your representation, you are saying that those extreme values doesn't exist because of the problem in your encoder. Maybe the encoder is the problem, and that is not an anomaly. That is what I was thinking. But the simpler question is how that builder or that encoder looks like. Do you have any example how to see that?
So this is a neural network. So a neural network can be looked as a big matrix of different weights between the connections. So let's say you have a huge matrix that shows the connection between different neurons and different layers of the neural network. And going from each layer to the others, the network is trained to learn the value of the weights. So by seeing the data, by observing the data and updating those values, it tries to actually fit the data as best as possible. Okay, in our case, fitting the data, meaning is the network should be able to reconstruct the data. So whenever you give the network a new data that is not seen by the network in the training process, using those weights in the matrix, it should be able to regenerate that.
To regenerate the data that you are with.
Yeah. So that is why I'm saying that that representation layer is actually describing the relationship between the input features, because using that representation, you will be, although you may not have the actual data, you will be able to regenerate data based on that set of, but based on those rules or those relations.
It seems like the performance of your model will be somewhat dependent on the amount of anomalous data that is in your data set. So it seems like it might look better if like 1% of the data is anomalous versus like 20%, because there's a lot on it that will kind of learn that representation is improvement. So I was wondering, do you have a sense of how the performance varies based on the amount of anomalous data?
Correct. Yeah. So for the data, we tried a very noisy data set, and this approach didn't work good. As you say, this one of the limitations of these approaches is the assumption of having the majority of the data to be valid. So if not, let's say you have a very noisy, very messy data set, those kind of noises will be considered as some normal patterns in the data, and it will be learned by the model. And so even if the new data point is anomalous, they would consider it as not anomalous. So yeah, this is a limitation of our approach, and the assumption, the pre-assumption for using this method is so we, based on the literature, we consider maximum 5% of data to be anomalous for this approach to be effective.
So depending upon what domain you're working with and what the problem is, the size of your inputs are going to be different. So how do you make decisions on the actual architecture of those different layers of the whole entire thing? Like, one layer going to be 3D, 4D, or I guess how do you make that decision, or is it automatically adapt to what it's seeing?
Yeah, so I have used an automatic approach that take a range of values for hidden layers and the number of neurons at each layer. It's kind of a brute force. It tries different structures, but it decides. But however, because I'm using another approach called dropout in neural networks, even if it is too complex network, it will consider some of those weights equal to 0 to avoid the complexity of the network. So after using that brute force approach that I'm talking about, you see that both less complex and more complex networks are having the similar result, kind of having the similar result because of the dropout metric that we have used. So that is why this structure does not affect the accuracy of the approach that much. So that is why we selected a smaller range of values for hidden layers and number of layers to make it less more I would say faster.
Yeah, great talk. So usually when you're training a neural network, you want it to generalize well. So you introduce regularization, drop out, early stopping, that's so well. So that it works well on novel data when it's easy.
Yeah.
It seems kind of like the opposite problem here though, because you don't want it to work too well on novel data. You want to be able to identify the anomaly. So I was curious how you change the training procedure if you use your standard methods for generalization, or if you do something, because it seems like overfitting is almost a good thing. You know what I mean?
So overfitting is not necessarily a good thing in that case. So even if you prevent the overfitting to happen if you have anomalous patterns in the data, we would expect that the reconstruction error of those anomalous subsequences or records be higher than the other records and subsequences in the data. So picking up the threshold is tricky to make sure that those data records are being detected as anomalous. But like I said, those approaches we use the regularization as well as the dropout metrics to avoid overfitting, and I think this is necessary because if it is overfitted, the anomalies wouldn't be detected as anomalies. Sure.
For the audience on the other side of the cyber internet, on Zoom, anyone have any question? Please go ahead, in the chat window, use the chat window, type your questions, or just unmute yourself if you have any questions.
Can I have a question?
Looks like nobody has question at this moment.
Can I have a question? Yeah.
Who?
Um,
Do you have a question?
yes. So, how can the framework deal with those false negatives? So in the
Sorry, I don't. I'll turn it up.
What is it?
how does the method deal with false negatives? So in the workflow, you have the expert to deal with the false positives. How does the method deal with the false negatives?
Sorry, I didn't.
Oh, okay.
Translate his question.
Can you please type it? It is
Yeah,
not-
so if you can type it.
Need to come there.
it is not-
Come from the ceiling.
Oh, okay. Could you please repeat your question? I think we have some audio problem. We have hard time to hear you. If you don't mind.
Oh, how does
In
the
the
method
chat.
deal with false negatives?
How does the method deal with?
False negatives.
Okay. Okay, so by false negatives, I believe you need the records that are anomalous and are not detected by the tool. This is correct because our approach, when domain expert inspect the output, the ones that he can inspect are the ones that are detected by the tool. Those are either actually false, which are false positives, and the ones that are, sorry, true positives, and the ones that are valid but incorrectly detected. Those two can be inspected and injected to the tool. But for false negative, we didn't have anything to do. However, after retraining the model, we evaluated all of these metrics, and we saw that even false negative improved over time after multiple retraining of the model, because we are moving from that unsupervised approach to semi-supervised. The learning method, after having this feedback, it can improve itself over time. I hope it has answered your question.
Okay, since any further question from our audience? No? Okay, thank you very much. Thank you.